I'm going to talk about what AEM is and some of the challenges that we have in QCing and modelling that data, and some of the inversion techniques that we've developed and released here at GA. Laurence is going to talk about some of the stochastic Monte Carlo inversions that he's just started taking us ahead with in the last few weeks. And Yusen is going to finish up with talking about some of the applications and the impacts of this work, and also about our AusAEM program. So let's move on. This is a slide to show how AEM works without any equations. So first we have a transmitter loop through which we put a either some sort of time varying current. It can be a sinusoidal one or some pulsed type current. Now that sets up a primary magnetic field, which when we have a receiver coil somewhere offset will get threaded by this primary magnetic field and induce a primary current in there. And then if we have introduced a conductive earth, electrically conductive I'm talking about here, not hydraulic conductive, then this time varying current will set up some eddy currents will get induced in the ground. Now those eddy currents will induce their own secondary magnetic field, which will also get seen in the receiver coil. And it's this voltage, the total of the primary and the secondary current, that we actually ultimately measure in AEM. So you can see that what we see is a combination of a primary magnetic field and a secondary magnetic field, which is indicative of what the conductivity of the Earth is. There's two main ways of doing AEM. One is frequency domain AEM. This is an example of one of the very first surveys I was involved in. It's a salinity mapping frequency domain system called Digim Resolve, and this was up in the Liverpool Plains area back in the early mid-1990s. Basically what these systems are 5 or 6 coils that are tuned to a very narrow band frequency of ranging from the tens of hertz through to hundreds of kilohertz, and we record the ratio of the in-phase and quadrature of the secondary field to the primary field. So that's ultimately what frequency domain data is recording. Now, we haven't used the frequency domain here much for GA's application because since some of the early salt mapping programs, because they only see quite shallow. It's the time domain systems which see much deeper. This is an example of a very large time domain system where a transmitter loop is slung around the aircraft and it tows a bird in which the receiver records the data. This is a helicopter-borne time domain system where the receiver and the transmitter are all slung below the aircraft in a towed assembly. And the next one, this is a different type of helicopter time domain system called SkyTem in this example. This one's been heavily used by the groundwater community here in Australia for surveys like the Broken Hill Managed Aquifer Recharge program. Very well calibrated system. And this is the Tempest system, which we're currently using for our AusAEM survey. So you can, if you've got very good eyesight, you might be able to see a transmitter loop slung around that aircraft. And if you follow it back here, there's a bird being dragged behind. Now, in this receiver bird, there's coils which will record very small magnetic field. Okay, so basically in the time domain system, we are putting through a current of this square wave pulsed type of nature. And essentially what we're doing is listening for the secondary currents to decay as they fade away. And ultimately what we record is a whole lot of voltages at different delay times after the pulse is turned off. In this particular case, we're recording what we call the X component, which is the horizontal component of the magnetic field, and the Z component, which is the vertical one. So there's different instruments inside that bird. So you can see that these systems, they're very varied. They're not off the shelf, and they're bespoke. They've been constantly evolving over the time since we started using them in the mid-1990s. In those times, they were bump finding machines. You did not have to apply, you couldn't apply qualitative inversion techniques to them. We've been at the forefront of trying to get those systems to be better calibrated so that we can apply quantitative techniques to them. And there's lots of challenges to that. AEM systems are, they work in a very difficult environment. You only got one chance as you fly over an anomaly at 65 metres a second or so. You don't get the chance to stack the data at one position. It's also turbulent and dynamic, so there's lots of vibrational noise, and you're moving through the Earth's magnetic field, so there's noise induced by that. So there's a lot of calibration and data processing that needs to go on with it. These systems, you can see they're big and gangly, so you can't really calibrate them easily in a laboratory. So calibration can be a bit of a problem. The quality control of the data is often, therefore, time-consuming, and it's not really a push-button type analysis. We can't just sort of make a script to go through everything and do it automatically. You have to analyse the data intimately. So on our recent surveys of our AusAEM, we've been able to encourage the contractor. Through our work in the past, we've managed to encourage the contractor to improve their system to measure new things. Typically, when we model AEM data, we need to not only take account of the thicknesses and conductivities of the Earth, we also have to take account of about 10 different degrees of freedom of what we call the system geometry. So that's the height of the transmitter, the roll, pitch and yaw of the transmitter, the roll, pitch and yaw of the receiver, and the three components of the separation between the transmitter and the receiver. Slowly over the years, we've, in our FROME Onshore Energy Survey, Onshore Energy Security Program Initiative, we saw the development of putting a GPS on the bird so that we could measure the positions of the receiver relative to the transmitter. In our recent survey, we've now got a gyroscopic inertial measurements units on the bird, which allows the contractor to measure the roll, pitch and yaw of the bird, which is the first time that's been done on a fixed wing system. But however, this picture over here is a close-up picture of one of those birds. So it's got this sort of shuttlecock arrangement on it as it flies through the air to create some drag. Inside this shell is 3 coils oriented horizontally, vertically, and transverse to those. And of course that bird moves around. Yusen will show you a video later of how that moves around. So we have to take account of that in our modelling. Now these IMU instruments aren't necessarily perfect for doing the job. One of the problems in the QA/QC of our most recent AusAEM survey, by closely looking at the data, we have found some issues that we had to spend some time to get the contractor to review their methodologies and come up with a better processing stream. So in this particular example, now that we've got that information on the bird, we are able to do more accurate modelling. At high altitude, we should be able to model the primary field measured by the system. We should be able, because there's no Earth that we don't know about when we're a kilometre above the ground, we can forward model what we expect to see. This is two examples from one flight. This is the top panel here, shows two different plots of the modelled and the observed data for a vertical component and the horizontal component. This is before the flight and after the flight. So you can see there's a bit of a mismatch between the two. And if we do it as a cross plot, you can see, for example, that these dots here are a little bit below the line where they should be, and these ones are a little bit above. Now that indicated to us, with a lot of analysis, that there was some pitch in that receiver bird or the transmitter loop that was not being accounted for in the processing. So what we've done is we've gone through we wrote some code to do some optimization, looking at all these different high altitude flights to find an optimal EM scaling factor and a offset for this receiver pitch data, just in a uniform search manner, and also another least squares optimization that showed that after we apply these calibration factors, we can get these data to lie on that line much better, and you'll see here that they fit quite a bit better. So this is one of the improvements that we've taken the contractor through, and we're pleased to say that now they're implementing this in their quality control workflow. This is another little thing that we picked up along the way. Those of you that have got a keen eye for geophysics will see that there's a slight parallax delay between, there's a slight horizontal shift between these plots. And through all of our modelling that we're able to do, we could do some cross correlations to find out that there was, in this particular case, a 3 sounding parallax shift. So the contractor was able to fix that up, and we actually found a programming error in the AEM system, acquisition system. So all those things go into, you have to do all that fastidiously before you can even start doing inversions. Now I'm going to show you my version of what's AEM inversion with this slide. We've got here a section of data from our Southern Thompson AEM survey VTEM. I've taken a sounding at 2 different locations. This location is this side and that location is that side. Here we have some data, some observed data in the red, and the blue model is an inversion model. So you'll see when the animation starts, it starts at a reference model. It starts down here at a very low conductivity value, and it slowly increments until the observed data matches the model data. And basically these 2 red soundings, this one and this one, to the untrained eye they look fairly similar. There's just a subtle change in the steepness at the start and the end. And that gives rise to this sounding have a much lower depth to the resistive material than this sounding here. So this is why these data are hard to interpret qualitatively. You need to interpret them quantitatively. So that's basically how our AEM deterministic inversions work, and we invert each of those individual soundings independently and then stitch them all together into sections like you saw at the bottom. So here at GA we've developed several different inversion programs over the year. They've been released open source on GitHub for industry and academics to use, and I understand through some of the feedback and questions I get that they're being used quite widely. The algorithms have evolved to solve some of the problems that we've encountered over the years. In the old days, it was hard to get a proper waveform and the proper filter characteristics from the contractors. It was sort of, they used to keep it secret because their systems weren't quantitative, they were only qualitative. And slowly we've worked through, as the industry has changed from incorporating new information of how the primary field is handled in the processing, how the different instruments measure different parts of the geometry. And we have solving for the geometry in our deterministic inversions. We've also more recently done trials of the lower base frequency AEM systems inversions. And then also along the way, we've improved our computational methods. When I first started doing inversion, it was a civilian science type of SETI thing where we had clustered computers, using people's desktops and offering a bottle of wine for whoever could invert the most samples, through to the GA clusters that we used to have, like Tornado and Cyclone, then onto the NCI, and then more recently, there's a lot of work being gone into, David McGuinness was a big part of putting the codes on the ANVGL, the National Geophysics Laboratory, so that external users that don't have access to compute resources can use it. And more recently, I've ported the code over to Amazon EC2. My intention is to make virtual machines available for industry because they don't want to muck around with compilers or muck around with large computational systems. We've got a few different types of inversion codes. I won't go through the details of that for this audience, but basically we have codes that can invert individual soundings by themselves, or through to codes that invert whole surveys at once, and that's what we've been able to take advantage of the NCI for doing that. I'm just going to explain one of our latest developments in deterministic inversion, and then Laurence will take over and talk about some of the new stuff that he's been doing with stochastic inversion. So this is a slide from a recent presentation at AEGC. So all our conventional inversions, we inverted one sample at a time in the time domain realm. And so the latest developments is that we can use the computational resources of NCI to invert a whole line or a whole survey at once, and then by doing that we can make some sort of constraints that are spatially or laterally constrained to make sure that each individual soundings model is similar to all the models in some sort of search radius. And also similarly, we can make boreholes have some impact on the inversion results, even if those boreholes are away from the flight line. I'll just show you an example of that I've applied on the Broken Hill Managed Aquifer Recharge survey. It is a comparison of our conventional deterministic invert one sounding at a time code versus the new code where we invert a whole, in this case I inverted a whole chunk of Broken Hill in one go. And you can see the main things to notice is that in this inversion, because it's only inverting one sample at a time, you get a lot of this vertical striping caused both by noise in the data and also by the uncertainty that is inherent in the AEM data. So by putting lateral constraints, we can make a more geologically realistic inversion model by making it coherent along the whole line. Now, that's where I finished, and Laurence will say how we're going to tackle some of this uncertainty.
All right. Thank you, Ross, and thank you, Yusen. Thank you, everyone. I'm just going to, as Ross said, talk a little bit about how we look at uncertainty. I'm not going to answer all of the questions about it. I'm more here to get you thinking about how we look at the data and how we should be thinking about the data and the uncertainty that we can derive from it, as well as possibly any other questions. So as you can see, there's been a lot of advancements in the data, in the surveys themselves, in the technologies, the new observations that we're measuring, especially the receiver geometry and the in fixed wing systems. We need to match this with our technology for inverting this data. So far, Ross has talked about his deterministic inversion. You've talked about running sample by sample or all at once inversions with lateral constraints, and they can be used to invert for these geometry parameters. But so far, our stochastic inversion code, which is quite advanced transdimensional inversion, which was first mentioned by Malcolm Sandbridge, not first mentioned, but mentioned by Malcolm Sandbridge a few weeks ago in a lecture he gave here. Also something that we're working on in collaboration with them, at ANU. Some codes have been provided for 2D models in the AEM sphere. But our current codes for 1D models currently don't have this capability for looking at these extra parameters. And so this is something that, even though we've looked at it in our helicopter system, something that we want to apply in our fixed wing systems. Now this is going to, I'm going to show you a few animations, and just these are just sort of to get you thinking about the problems that we're facing. So this is an older real data inversion from a system known as SkyTem, a helicopter system. And I'm just going to take you through some of the items on this inversion as it's progressing. So what this is that we try many different types of layered Earth models. In this, as you can see here, this is a conductivity versus depth map. And you can see in the background here, we've already got the solution. This is a posterior probability distribution, likelihoods of conductivity with depth. And along down the side here, we have counts of essentially likelihood of there being a layer interface at these particular depths. So as this inversion is progressing, as the samples are increasing, we have what's called a Markov chain of a model, which it essentially wanders around the model space, and it's jumping between the number of layers. As we can see here, we've got different histogram of different numbers of layers as they are counted up. And you can see here these models are between 3 and 10 layers. And as this is jumping around, it's sort of recording in this histogram. Once it passes this little line here, this burn-in line, and as we can see here, the fit between the model data, these blue and red curves, versus the measured data. So sorry, the full model versus the measured data. The measured data is the one with the error bars, and so we can see here that these curves are sort of dancing around within the error bars, and that's exactly what this type of data processing, this type of inversion is meant to do. Is it's meant to not just give you the best or lowest misfit, trying to drive this down as much as possible, but to actually just try and describe the entire thing, show all of the likely models, and those that are most likely are most coloured in, and those that are less likely are less shaded, down to pretty much what is not likely at all. So I hope I haven't confused you too much with that one, because I'm going to move on with this concept and try and build it up a little bit more. So as I mentioned before, we have new information that we need to look at. AusAEM, we are now measuring all of these geometry parameters, and we know that there are some which we want to investigate. We want to investigate sensitivity on these parameters with regards to our forward model, with regards to our 1D models, and we want to see if that matches well with what we're measuring, to see if there's any bias in what we're measuring, if there's any instrument error that we're not uncovering yet, and also to examine any trade-offs on this. And so the parameters that we're going to investigate here, and that I've been initially asked to investigate, are just these three. That is, for the receiver bird, the offset from the transmitter loop, so the difference between longitudinally, I think the dx and the dz are vertical and horizontal. We're not so concerned about the dy. We know it's not as sensitive. And also, very importantly, the tilt or the pitch of the receiver bird. This parameter is measured by the IMU on the receiver bird, and that's something that we really want to make sure that we're getting right, or at least is being delivered to us correctly, and if not, we need to know how to correct it. So this slide, we're looking at our existing algorithm, our existing transdimensional inversion algorithm, solving for the number of layers, solving for the conductivity profile, and we're seeing two chains here, so it's advancing at a rapid pace here, so it'll loop around and repeat in a second. But we can see here that these two chains, they're trying to drive this misfit down. It's not getting down to where we want it to be. It's not within the margin of error that we're happy with. We can see after the burn-in, it's starting to colour in the likely conductivities, but we're not too happy with it. Most importantly, I'm not happy with what's going on over here. These are the geometry parameters, the dx, dz, and the pitch, and we can see here that they aren't moving around much. They're sort of stuck where they are. They're not describing anything, and this is what's commonly known as a tuning problem. So this is requiring a fair bit of effort to get it right. So what we've been aiming to do, well, first of all, comparing it with as after 50 chains and 50,000 samples per chain, what does the result look like? Well, we have this sort of smudge of a posterior distribution, and this is actually a synthetic example. We can see some chains got converged and some chains got stuck. And because this is a synthetic example, we know the true model. And I know that I set the dx and dz of the offset of the receiver bird to minus 110 and minus 45 metres. And I know that I set the pitch to 4 degrees. Now, unfortunately, it doesn't seem to be describing particularly well a distribution in these two parameters. In this dx, it seems to be converging quite well, and this is sort of reflected somewhat in the poor misfit of some of these chains, and also slightly incoherent, rather uncertain looking posterior distribution we have here. So, if we want to describe uncertainty, we need to be a little bit smarter about it. So what do? We try another technique. This is a different inversion algorithm. It's similar to what I previously described. It's called sequential Monte Carlo, which, don't let the name confuse you, it's actually highly parallelizable. So the sequential refers to a mathematical aspect of the algorithm, which is related to one of the essentially a sampling step. And what we notice here is we have a whole lot of chains, essentially a cloud of what I have is 1,000 models going at once, and we start off with what it looks like television static, and everything is broad. Everything is essentially what we've done is we've sampled the prior, and then we've asked it to coalesce on the correct solution. So as it's progressing along, we can see that it's I guess I wouldn't say converging, but stabilising reasonably well to what we know is going to be the true model at 60 metres depth. And so I'll just move on to the what we can see as the final solution here, and we can see that the geometry converges quite well. This is a self-tuning algorithm. That's a fair bit of work has gone into this, and also it's within error of what we know to be the true model as a synthetic solution. You can see that these are, I just want to highlight here, you might think that these are broad error bars here. It's a visual illusion. The fact that this is a log scale, this is not the difference between 10 to the minus 4 and 10 to the minus 2, if you think about it, it's not that big. So it's quite close to what we describe as the true model, and especially in the high conductivity ranges it is again. That's all very well and good if we're looking at synthetic examples, but how does this apply to real data? So we have some real data. We have measured data from AusAEM. And I've taken, I guess, a simple example using the sequential Monte Carlo and said, okay, how do we apply? I said, well, it doesn't look as nice as a synthetic inversion, but it's still going to require some tuning. This I did last night, so it is pretty fresh. You'll see that the misfit is being driven down on the whole. It's not getting quite right, so we know that there are some things we're not modelling perfectly. We're only looking at these geometry parameters, so there's probably might be more to investigate. In human time, though, instead of taking that previous Markov chain Monte Carlo was not very parallelizable. It takes between 10 minutes and 2 hours, depending on how many processes you want to run it on. This took 2 minutes. I ran it on 100 processes. So I don't mind how much computing time I'm using. And so we have a large computer, we're going to be able to use it. We can see that the pitch does in fact converge. I'm quite happy about that. Something we might need to address a little bit more, the offset of the receiver bird. But in general, it's looking okay. What we can notice about this is this is a nice, I'm a happy geophysicist. This is a well-constrained resistive basement. I'm happy that I know that I can see where it is. This is good. Unfortunately, not all data looks like this. So when we have conductive cover, AEM as a technique starts to not be able to see what's beneath. This on the right here, we can see this is an early result of a deterministic inversion that Yusen had done a few months ago on the AusAEM data, and we can see here using one particular reference model and not solving for geometry, we get one particular kind of basement, and using either a different reference model or solving for geometry or some tuning in the deterministic parameters, we're starting to see something down here, and we think, is there something down here? We're running it through the Monte Carlo inversion. We can see that we don't really know what's down there. It also doesn't converge quite well, so we do know that there's something which is not quite right here, and it looks like it's the receiver pitch. I left the prior about 10 degrees wide on this, and it's still moving off. So I'm not entirely sure if it's the receiver pitch or something else which is going wrong. But again, I can run this in 2 minutes. I can change something. I can go back and I can have another look. But at this stage, we can see that it's very clear about the conductive cover, but it has no idea. After about 200-300 metres, we're starting to get down to what we don't know. And this raises the question, what are we trying to ask here? This is something that that Malcolm did ask here, raise here, in his talk a few weeks ago, is that inversion doesn't really necessarily tell us the answer, but it tells us how to sharpen the question. So how do we interpret uncertainty? Here is a section inverted using sequential Monte Carlo. We have the mean model, and we have the spread from the 10th to 90th percentile. How do we combine these two? What can we use out of this? This is just an off-the-cuff example. Not necessarily. This is not going to be canonical, but we need to be able to exercise this data properly to see what can we see versus what can't we see. And so I'd like to wrap up with that and say, if we are going to be sharpening the question, what are the next steps? We have more data, we have more inverted models, we have more information. How are we going to interpret this? Well, the next steps, to me, clearly would be, should we try some quantitative interpretation, including the application of machine learning, data assimilation with other techniques. We do need to put some more work into the robustification of the codes. Sharing the knowledge, definitely, is something that, that at the moment we have to get our new developments out there. And we need to be able to pose to the agency, what are the questions we need to ask about this data and how are we going to ask them?
Thank you. Okay, now I'm going to show you some pretty pictures and try and push through the last part of the talk. So bringing you back down to earth, what are we actually measuring? We're measuring conductivity. So conductivity is a physical property from the earth-forming materials that allows electricity to travel or not through them. So when we show you all these fancy sections of reds and blues, what we're actually trying to do is a translation between values of conductivity and real earth materials. So this is like our dictionary, all right? Okay, just very briefly, I'm gonna talk you a little bit about GA's involvement with Airborne EM Ross mentioned it briefly at the beginning. But here is a map of Australia, of course, and the different coloring show a whole bunch of surveys that have been flown through time. The blue ones are back in the 90s, and then we go to the dark red ones, which are the current ones. You can see the dimension, how they've grown, and sort of our applications have broadened. It's been quite a remarkable journey, I think. I've been part half of it, potentially, but we are seen as an agency that is pioneering a lot of these techniques worldwide, and sort of we are constantly being consulted in other countries about how we're going about it. Just a few of you would be familiar with some of the first ones that were for mapping salinity, then the onshore security programs, which are the yellow ones, the FROM. And these surveys that were flown 10 years ago are still having impact. So I'll try and show a little bit about that. So the surveys we're flying today, don't expect them to be relevant tomorrow, but they'll trickle on 10 years away from now, which is quite important because that is only an agency of this nature would be able to fly these kind of surveys, right? A little bit about the modeling. These guys have talked a lot about the modeling, but one thing we have pushed is with the survey providers, we need to know the intrinsics of your instrument. So this is a very complex chart. I don't pretend to go through, but I hopefully by now we've shown that there's different geometries, different arrangements, different platforms. You can fly on a helicopter or on a plane. And if you know all of these, then you can actually model and get a quantitative analysis of what you're getting. So this is what I'm trying to get to with this. So in order to do this, we've established a calibration range out in Broken Hill, where we are not satisfied with a contractor that comes out and tells us, I've got the biggest hammer, I don't have the best instrument. It's like, let us assess it. And this has been a very hard job, seriously. At one stage, they wouldn't give us the waveform, which is actually the form of the pulse that they pulse the ground with. And with that the modeling is even more airy-fairy than what it currently is talking about uncertainty, right? So this is a place we've established in Broken Hill. We've got all the contractors to fly over these. I'm going to show you an example. And this has sort of established GA's credibility out there in the industry and worldwide, because we have a deeds of stand which says if you want to fly for any government agency, and that's where we sort of have a lot of collaboration with CSIRO and the states and territories, they come and say, GA, can you help us set up the next survey, because we know you guys have the standards, right? So we fly this and then we model. We don't sort of rely on what they've said. We have prior information like passive seismic and down-home bores. And I'll just show you a brief example. Remember, blues are resistive areas, sort of crystalline bedrock. This is a lake, that's the Menindee Lakes, which has been an important part. And what we have is 3 different instruments, or two flavors of one instrument and a different instrument. But now we have all the system providers have flown over this patch of ground. And you can see, like if these are boreholes, you can see, if we call them sort of our ground truth, we have generated through modeling a quite seamless section. So we have quite confidence that we are modeling and that the instruments are actually reflecting what we want them to map. So why do we use AEM? Australia is very extensive, has a quite extensive cover, over 80%, right? So a few years ago, Richard Blewett and the team went over to Adelaide and talked to a whole bunch of geophysicists, academics, and consultants. And they said, what would be the ideal method to map undercover? There's not much outcrop in some of these areas. And there's details about that talk, but AEM was determined to be the optimal technique to be able to map undercover. the fact that all this potential is undercover means that Australia is quite underexplored. And AEM is a great reconnaissance tool. Here, what we're showing in the bright colors are how the outcrop is quite limited. We've seen that most of the mines and deposits are in the bedrock-dominated areas, and how the regolith is in pale colors. So we're trying to determine ways where we can continue the geological features under the cover. What this means is there are great opportunities for new discoveries. So now I'm going to briefly show you a video of Tempest, and why I'm going to do that is because the Tempest system, which is the one we have used to fly our survey, I'll play the video so you can get a feel of a few things, of the sort of land we're flying over, what the instrument is doing, but I also taken the opportunity to talk a little bit about a CRC. This instrument was actually developed in Australia, and by one of our very own geophysicists, who's Richard Lane. So it's very important. It's an Australian development. The instrument was designed for the Australian conditions. It came out of CRC, the CRC AMET, which operated with government funding since 94 to 95. This is some notes Richard put together for me so I could share with you. It has been used for a variety of applications, as we've talked, like mineral exploration, land management, and groundwater. It was one of the first to establish quantitative standards. And it was sort of seminal in allowing GA to proficiently map the conductivity of the upper few hundred meters, as we sort of talked about. So you can see a lot of this video shows that the ground where we're flying over has really no outcrop, and the quantity of data we are acquiring is quite remarkable. So now I'm going to show briefly the AEM. This is a survey. Here are the flight paths of what we've flown. And on the background, as we said, this is the biggest airborne EM survey flown in the world so far in area. It's the size of nearly France and Germany combined. We've flown a large amount of it. We just did the first release, and this is what it looks like. These are conductivity sections. As you know, it straddles between the Northern Territory and Queensland. This data just arrived 2 days ago, so we've managed to image it. But it's massive amounts of data. I mean, we're talking of millions of points. Each of those inversions that Laurence talked about was one sounding. So imagine handling the data millions of times to try and retrieve those sort of images. This first tranche was released by the minister in Perth a month ago, and sort of one thing we've done has been trying to acquire the data and make it publicly available as it goes, which has been a quite successful way of doing it. So what are we really able to resolve? Remember, these are 20-kilometer spaced lines. This is being labeled by some of our colleagues, Pauline, back there. So really interesting features. For instance, you can see a clearly defined fault. That's a Tanami fault. It's actually giving us a lot of insight of where the basin boundaries are. This is quite interesting. When we talk about cover, I would like to draw your attention to these lines. So this yellow line is a feature that extends over several hundreds of kilometers. So it surfaces, then we would lose it if we were just standing on that ground. But you can see clearly it's continuous over several hundreds of kilometers. Interesting features. So we need our geology goggles to try and explain what all of these things mean. From a regolith, that's a radiometric map of Australia. The pale colors here are usually related with transported cover. Of course, the AEM gives us the second and third dimension. So those white lines are a paleo channel. When we expand it, you can see now we can start quantifying volumes and sort of amount of sediment or potential groundwater in the area. One thing we've had to do is these lines are so long, 900 Ks. This is an animation Ross did. So we're looking at little blocks to try and identify and sort of determine different features. We've had to be very innovative to try and see how we handle these large amounts of data, right? So I won't show you anymore, but that goes over 900 kilometers, right? The next thing we've done is, okay, how is one person going to look at that? So let's look at sort of quick ways where we use machines. So these three are inversions model, or call them models, from what Ross talked, and we call them covariates. Then we feed it to a machine, and the machine learning helps us do a classification. This is work we've done with some other colleagues like John Wilford and Niket and some of the other guys. Quite successful. We showed this at AEM in Denmark. People were very impressed. Other things, very briefly, is there's another parameter that is not conductivity, which is induced polarization. So basically, there's some materials, for instance, in South America, in the Andes, particularly where there's a response that charges the energy as a battery and then slowly releases it. What that means is that we see in our standard response a bump which is negative. And this has been sort of present in the industry for a few years, but currently is sort of a big hot topic because it gives us another weapon or another tool to try and distinguish between potential mineralization. And now with Jay's coding, with Ross's coding, and we're going to throw a Monte Carlo at it with Laurence, we can actually model that. So we're keeping up there with industry and the academics at quite a leading pace, which is good to see. I'm going to show you two examples and I'm done, about earlier impacts. So those are one of our, some of our surveys that were flown 10 years ago, 2007, 2008, particularly Patterson. And just briefly, in AMEC earlier this year, Encounter Resources showed a bit of information. So that's a section from the Tempest, which is a system I've flown. And they encountered copper, right? So they determined this area B1 to be of importance. Then they reported a finding they drilled actually some of those anomalies and around the area. Of course, EM is just attracting them to the area. Then they do the geochemistry and other things. And sort of 2018, they've just reported important mineralization in the area. So industry is coming up back saying, thanks guys, those things are driving us to different areas, which we know, which has been interesting. Another thing is, this is a byproduct, so it's a map of cover thickness. So maybe Richard Lane, you remember this survey. This is one of the very first commercial surveys flown in the Musgraves. So the Musgraves is that area between Western Australia, Northern Territory, and South Australia, quite remote. And this was flown from a minerals perspective, right? But then we reprocessed it. And you see those dark dendritic patterns? Well, those actually host quite a lot of water, and they're being used now and extracted by Aboriginal communities to support some of the livestock and other things, which is interesting how these data, when properly managed, it has a lot of legacy and can be used for the future. But also, it's really important for us because it's a map of cover, right? The darker parts is where the cover is thicker or not. A little bit of how we engage with other agencies, because I think that's important. Funny enough, we are sort of, sometimes we feel we're sort of contributing to the R&D of some of these providers, the work that on the recent AEM on sort of modeling all those pitch and rolls is now being picked up by this industry and sort of streamlined in their processes. We do a lot of work with the CSIRO, academics and universities, strong collaboration with the state and territory geological surveys. There's other agencies that come and ask us for things like agriculture agencies and groundwater agencies. Industry, constantly we're interacting to industry. They're asking what our standards are and sort of trying to see what we establish on our deeds. And recently some other geological surveys like the USGS are going to start to fly the whole Mississippi. And they've asked us to go and sort of share our experience. Funny enough, they're bringing the Tempest, which is an Australian system, to the US to try and help them map, which is really nice to see. And just to finish up, some of our take-home messages. We've heard a lot about the QC and how it's difficult but important. It's sort of the grudge work that's done there. Sometimes you'll see Ross, Laurence, and I just chugging away doing this horrible thing, but it's important. So now we have codes that are open source and available for the industry. The Monte Carlo is really crucial because we're assessing the probability and the robustness of our models. So we're not taking one model as bliss. We're sort of exploring a wide range of models, and that's been really good, supportive. I think we have a bit of impact in the exploration industry, our state partners and other geological surveys like the USGS. And these regional data sets have proved to unveil features at a scale that has never been seen before. So as you know, one of our crown jewels is our magnetics and gravity maps of Australia. So we're working towards coverage a la gravity or a la magnetics like that. Right, and that's it. Thank you very much.